5 moons in our solar system have what life actually needs to survive, and they might be better at hosting it than Earth ever was. Forget Mars. The real estate for alien biology isn't on planets at all. It's frozen worlds orbiting Jupiter and Saturn, hiding oceans under miles of ice that have been liquid for 4 billion years. Picture an ocean twice the size of all Earth's seas combined. Pitch black, no sunlight has touched that water since the solar system formed. 10 miles of ice overhead. And it's warm down there, not from a sun, but from gravity itself squeezing the moon like a stress ball every time it orbits its giant planet. Something could be swimming in that darkness right now. Life needs 4 things that don't usually go together in space. Liquid water, which freezes in the void. Energy, which the vacuum doesn't provide. Organic chemistry, which requires both water and energy to function, and protection from radiation, which rips molecules apart before they can build anything complex. Planets try to offer these and fail spectacularly. Mars lost its water to space. Venus boiled its oceans into acid clouds. Earth barely threads the needle, and even here, life almost died several times. But moons figured out a loophole. They don't orbit stars, they orbit massive planets, and those planets crush them with tidal forces every single orbit, kneading their interiors like dough, generating heat from friction alone. The ice on top becomes a shield, the ocean below stays liquid, and the chemistry gets weird in all the right ways.
Europa is the crown jewel, Jupiter's 4th largest moon, covered in cracked ice that looks like a shattered windshield. Beneath that frozen shell sits an ocean with twice the volume of every drop of water on Earth combined. The ice is 9 to 15 miles thick, more than enough to block the radiation belt surrounding Jupiter that would kill you in hours on the surface. 15 miles of ice cuts that radiation down to nearly nothing. A few meters below the cracks, it's quieter than a deep-sea trench on Earth. Water too. Tidal heating from Jupiter's gravitational squeeze keeps the water liquid despite being 5 times farther from the sun than Earth is. Here's the math that makes Europa terrifying and exciting at once. Jupiter's radiation belt is so intense that standing on Europa's surface exposes you to 500 times Earth's radiation per day. Your cancer risk would spike within weeks. But water is an incredible radiation shield. Every meter of ice you go down cuts the radiation in half. By the time you reach 10 feet under, it's already reduced by over 90%. By the time you reach the ocean miles below, radiation is irrelevant. Meanwhile, the ocean has been stable for potentially billions of years, longer than multicellular life has existed on Earth. If life started there, it's had time to evolve, adapt, and spread.
Pause right now and think about this. Would you bet on Europa having life, or would you bet against it? The ocean is there. The energy is there from tidal heating. Organic molecules probably exist. Comets have been delivering them for eons. The environment is stable. What's missing? Nothing we know of. So what's your answer? The problem is we can't easily check. Europa's ice is miles thick. Any mission would need to land, drill through kilometers of frozen crust, melt through without contaminating the ocean, then deploy a submarine in pitch black water under crushing pressure. It's the hardest place in the solar system to explore, which is why Enceladus changes everything. Enceladus is Saturn's 6th largest moon, barely 300 miles across, small enough to fit inside the width of Texas. But it does something Europa doesn't. It vents its ocean into space. Geysers erupt from cracks near the South Pole, shooting ocean water at over 1,000 miles per hour into the vacuum. These plumes contain water vapor, ice crystals, salt, and organic molecules. Scientists have detected methane, carbon dioxide, ammonia, all the ingredients for chemistry that could support life. You don't need to land. You don't need to drill. You fly through the plume with instruments, collect samples, analyze them on the spot. It's an ocean you can taste without ever touching the surface. The geysers proved the ocean exists. The salt content matches what you'd expect from a seafloor in contact with rock, meaning chemical reactions are happening down there. Hydrothermal vents, maybe, like the ones on Earth's seafloor where life thrives without sunlight. Those vents pump out heat and chemicals, creating energy gradients that biology can exploit. If Enceladus has vents, it has everything: water, energy, chemistry, and time. Which moon is most likely to have life right now? Europa with its massive ocean, or Enceladus with its accessible samples and confirmed chemistry? The honest answer is we don't know. Europa has more water, more volume, more time. Enceladus is easier to study and actively shows us what's inside. Both check every box. Both could be dead. Both could be teeming. The question isn't which one is better, it's which one we investigate first. Titan rewrites the rules entirely. It's the only moon in the solar system with a thick atmosphere, 1.5 times the pressure of Earth's air at sea level. That atmosphere is nitrogen and methane, and it's cold enough that methane rains out of the sky and pools into lakes. Liquid methane lakes. Hundreds of them scattered across the surface, some as large as Earth's Great Lakes. Titan has weather, seasons, river channels carved by flowing liquid. It's the most Earth-like world we've found, except everything familiar is made of the wrong substance. Underneath that methane landscape, Titan likely has another ocean, this one made of water, deep underground, kept liquid by tidal heating from Saturn just like Europa and Enceladus. So Titan offers two chances for life: water-based biology in a hidden ocean, or methane-based biology in the lakes on the surface. If life exists in those methane lakes, it's not life as we know it. It would be chemistry operating at minus 180 degrees Celsius, using liquid methane as a solvent instead of water, running on completely different reactions. If we find that, it doesn't just prove life exists elsewhere, it proves life can work in ways we haven't even imagined. Think about that choice for a second. Would you rather discover life that resembles Earth's biology, water-based, familiar, something we can understand and relate to? Or would you rather find methane-based life that forces us to rewrite every textbook and expand our definition of what's possible? Both answers are right, both are valuable, but they're emotionally different. One is confirmation, the other is revolution. Callisto sits farther out from Jupiter than Europa, which makes it less interesting at first glance. It's older, more cratered, geologically dead on the surface. But that distance is its advantage. Callisto receives 400 times less radiation than Europa does because it orbits beyond the worst of Jupiter's radiation belts. If you're building a base to study the Jupiter system, Callisto is where you land. The surface is safer, the ice is just as thick, and magnetic field measurements suggest a subsurface ocean exists there too, probably salty, maybe in contact with rock. It's not as dramatic as Europa's fractured ice or Enceladus's geysers, but it's potentially habitable, and it's far easier to access without killing your crew with radiation. Triton is the outlier. It orbits Neptune, the farthest giant planet, in a retrograde orbit, backward compared to Neptune's rotation. That orbit is tilted and elliptical, which means Triton gets squeezed and stretched just like the moons of Jupiter and Saturn. That tidal heating might be enough to keep a subsurface ocean liquid despite being 30 times farther from the sun than Earth. Triton is the coldest place in the solar system with active geology. It has nitrogen geysers that vent gas and dark organic material onto the surface. If tidal heating can sustain an ocean that far out, in that cold, it expands the possible habitable zone to the edge of the solar system. It suggests that life doesn't need a star nearby at all, just a big planet to orbit and the physics of gravity to generate heat. You're funding one mission in the next 20 years. You can send a probe to Enceladus and fly through the geysers. Quick, cheap, immediate results. Or you can send a lander to Europa and drill through miles of ice to reach the ocean directly. Slow, expensive, but definitive. Which do you choose? NASA and ESA have already decided. They're going to Enceladus first. The accessibility wins. If the plume samples show clear signs of life, it justifies the cost of drilling into Europa later. If the samples are sterile, it narrows the search. It's pragmatic. It's not romantic, but it's the right engineering choice. The irony is almost offensive. We spent decades obsessing over Mars, a freeze-dried corpse of a planet that lost its atmosphere and oceans billions of years ago. We built rovers, landers, orbiters, and habitats for a world that's hostile to life, and has been for longer than complex life has existed on Earth. Meanwhile, moons with active oceans, organic chemistry, and energy sources have been orbiting the gas giants the whole time, waiting for us to notice. The places that look most dead from a distance, frozen, airless, billions of miles from warmth, are the places where life has the best shot. Not in spite of the ice, because of it. The ice is armor, the ice is insulation. The ice is why the oceans are still there after 4 billion years. We might be decades away from knowing for sure. Missions are launching, instruments are being built, spacecraft are en route or in design. Within your lifetime, we'll fly through Enceladus's plumes and analyze what's inside. We'll map Europa's ice and look for thin spots to drill. We'll send a drone to Titan and sample the lakes. And when the data comes back, it will either confirm we're alone, or it will prove that life is common, resilient, and capable of thriving in places we thought were impossible. Either answer changes everything. But only one of them means the universe has been full of life this whole time, hiding in the dark, under the ice, waiting for us to look.